Hello viewers, welcome back to our series of lectures on photochemistry. Today in this concluding part of the series, we will take up two things. One is the quantum yield or quantum efficiency, and the second aspect we want to take up today is the quenching mechanisms. The session is planned as follows, that is, to begin with we will briefly review what we did in the previous sessions. Thereafter we will try to recall what are the photophysical processes we have learnt about earlier, because that is going to be of use to us in today's session. Thereafter we will come down to the first main theme of today's session, that is the quantum yield. We will try to define what it is, and then thereafter we will see that how do we make a measurement of quantum yield. In this process, in this context rather, we will take up what is called as actinometry. We will talk about how do we use a chemical actinometer to measure quantum yield of a photochemical reaction. Thereafter we will try to bring in what is meant by fluorescence quantum yield. Thereafter we will bring in the concept of quenching and see what do we understand by quenching, then what are the mechanisms by which the quenching takes place. Thereafter, in this process we will primarily talk about two kinds of quenching mechanisms. One is the collisional quenching, the second happens to be resonance energy transfer. There are two mechanisms by which the quenching primarily takes place. Thereafter we will take up what is called as photosensitized reactions, wherein we will try to put quenching, an undesirable phenomenon, to a practical use over there. And then towards the end we will try to sum up what we do in today's session. Okay. So, with this as an outline, let us try to make a beginning by recalling what we did in the previous sessions. What we have done so far is, we started by our discussion by defining what is photochemistry, and then thereafter we differentiated between what are the photochemical reactions and what are the thermal reactions. The different aspects of it we took up there. Thereafter we explained the fundamental laws of photochemistry and discussed their significance. There are very significant laws we took up there. Thereafter we discussed the consequences of absorption of radiation by atoms and molecules. Basically what we did there was that if I have got atoms or molecules and if I give some radiation to that, what kind of consequences are there. That means primarily we talked about the electronic excitations, and in case of atoms it is only electronic excitation, whereas in case of molecules the electronic excitation was coupled or accompanied by vibrational and rotational transitions as well. Then we discussed what is the fate of the electronically excited state. That means if I have a molecule, I have given a radiation to that has become excited, it has become electronically excited, then what can happen to this molecule which is excited, how does it relax back. So, all that we did in terms of what is called as a Jablonski diagram. Then we took up two very important phenomenon, that is of the fluorescence and phosphorescence. We defined what they are, we explained the origin of them, and then discussed their characteristics, because they are very crucial phenomenon for us. Having done that, we moved on to two closely related phenomena of chemiluminescence and bioluminescence, and described an application of these in terms of an environmental determination. Okay. So, that is all what we have done so far. Today we will continue from here, and we want to talk about quantum yield or quantum efficiency. To come over to that, let us first start with what we understand by photophysical processes. As the name suggests, photophysical processes, that means we are talking about some kind of physical changes there. So, primarily the photophysical processes are the ones, they are the processes which occur subsequent to excitation. That means you have a molecule, you give a radiation, the molecule gets excited. So, what happens to this molecule thereafter? So, that basically is that how does it relax down, what are the physical means of relaxation. And then this basically involves two kinds of things. One, that means this relaxation from an excited state to the ground state could be accompanied with some kind of an emission of radiation, or it could be just without that. That means you can have thermal kind of relaxation and things like that. And the basic thing here which you have to take note of here is that there is no change in the chemical structure or nature of the molecule. That is the basic thing which differentiates between a photophysical and a photochemical process. A photochemical process will be the one wherein we absorb radiation, a photon is absorbed and a chemical reaction occurs thereafter. So, that is a photochemical process. And what we are now referring to is a photophysical process. So, the two are, both of them take place and both of them are very significant here. Okay. Now, let us look at these photophysical processes which were done earlier also. One of them happens to be vibrational relaxation. That means you have got an excited molecule here, say in a singlet state here, it just relaxes vibrationally. That means from an excited electronic energy level as well as excited vibrational energy level, it comes down to the ground state of that. That means still remains electronically excited, but it vibrationally relaxes down. That is one of the mechanisms. This is a non-radiative mechanism. Another one is what is called as internal conversion. That means a molecule which is in excited singlet state here, say this state here, this can go to another singlet state which again is excited one. This is called as internal conversion. We go from singlet to singlet or triplet to triplet, that is called as internal conversion. The third possibility of a photophysical process is what is called as intersystem crossing, wherein what happens is the molecule, say from a excited singlet state, goes to an excited triplet state here. So, singlet to triplet, intersystem, that is the meaning of this particular transition here. That means there is a transfer of a molecule from a singlet state to a triplet state or vice versa. Normally, the reverse is not that often. Primarily, we do come across what is called as a singlet to triplet transition. Another possibility of a photophysical process is what is called as fluorescence. This is a one which is accompanied by a emission of a radiation. All the three processes we mentioned earlier, they were non-radiative processes. This is one radiative process where a molecule in the singlet excited state comes down to a singlet ground state here with the emission of a photon here. And then the last one here we discussed earlier, what is called as a phosphorescence, wherein a molecule in the excited triplet state comes down to singlet ground state with the emission of a photon. So, they are the processes we have discussed in detail in the previous sessions here, but in addition to that there are two more processes. One is called as collisional deactivation. We will talk about this as you proceed further, and second is called as energy transfer. We will talk about these in the context of quenching. Okay. So, they are the physical processes or the photophysical processes which we need to recall. Okay. Having done this, let us move further and see what do we mean by quantum yield. In order to understand the meaning of quantum yield, let us go little backwards and try to recall that as per the laws of photochemical equivalence, a molecule absorbs a single photon during excitation. That is what we learned in the first session here. That is, you have a molecule will absorb a photon and become excited. A given molecule will absorb only one single photon. That is very, very crucial. That is called as a law of photochemical equivalence. Now, suppose there are 100 molecules and each one of them absorbs a photon and becomes excited, and each of these excited molecule, if undergoes a photochemical reaction, then the number of molecules which will be reacting will be equal to the number of photons absorbed. That means 100 photons absorbed, 100 molecules reacted there. So, however, what happens is we find that the excited molecule either forms a photochemical product or it decays to the ground state by radiative or non-radiative process, the photophysical processes we just discussed here. That means, it is not necessary that any molecule which has got excited will undergo a photochemical process. If it so happens that all the molecules undergo photochemical process, then of course, whatever is the number of photons absorbed, that will be the number of molecules which have got reacted through. But since we also have photophysical processes accompanying them, what happens is we expect that the number of molecules which will react as a consequence of photoabsorption may not be equal to the number of photons absorbed. So, that is going to be different, and then this difference actually is quantified in terms of a parameter called as quantum yield or quantum efficiency. This basically is defined as follows. We give it by a symbol phi, and is defined as the number of molecules which undergo chemical reaction in a given time. That means, you have a reaction vessel, you give light to that. So, you pass the light for a given amount of time, then see in that amount of time how many molecules have undergone the reaction there. And then of course, we take on the denominator we take the number of photons which are absorbed in the same time. This ratio of the molecules undergoing the reaction to the number of photons absorbed in the same time is called as quantum yield. If we really look at it in terms of the conceptual part of it, this basically refers to the number of molecules which undergo reaction per quantum of the absorbed energy. Suppose one photon is absorbed, how many molecules undergo the reaction? If it is 1, its quantum efficiency will be 1. If it is more than 1, it will be more, and so on and so forth. Just let us try to do an alternative representation of the same expression. We know that 1 Einstein of energy is the energy of 1 mole of photons. So, if I just put that, I can define quantum efficiency or quantum yield to be equal to the number of moles of chemical reaction occurring in a given time divided by number of Einsteins of photons absorbed in the same time. It is an equivalent expression here. The only thing is there we talked about number of photons per se, here we are talking about number of moles of photons here. The ratio remains the same thing. And typically what is observed is this value of phi is observed to be anywhere from 0 to as high as about 10 to the power 6, which is a very wide range. And that is the range wherein we can find the quantum yield or quantum efficiency or different reactions to be. Let us look at that, though this is what is observed, but generally what you find is that the quantum yield or the quantum efficiency is found to be quite low, which is understandable, because quantum yield is low means part of the molecules which got excited are undergoing chemical reaction and others are decaying by photophysical processes. So, that is understandable. That means the number of molecules which will undergo chemical reaction may not or are not or lesser than the number of photons absorbed there. But how do we account for the higher values? The higher values of quantum yield arise due to a sequence of thermal reaction initiated by a excited molecule. Let us understand this. Let us take an example here. Let us take the example of photo decomposition of Hi. This is found to have a quantum efficiency or quantum yield of 2, which means for every photon absorbed there are 2 molecules of Hi which undergo decomposition. How do we account for that? We account for that in terms of the following mechanism. The mechanism goes as follows, that is, you have a molecule of Hi which picks up a photon, undergoes dissociation like this, it gives you free radicals here, H radical and I radical, and this H radical then reacts with another molecule of Hi to give you Hi, H2 and I radical again, and this 2 of these I radicals combined together in presence of another molecule then gives you I2 and this molecule gets excited here. So, in this whole process, in this mechanism, what you see is that there are 2 molecules of Hi are reacting together and they are giving you H2 and I2 here. In terms of the number of photons absorbed, so there is only 1 photon absorbed here and 2 molecules of Hi have reacted in this whole process here. So, as a consequence, we see that the quantum yield for this particular reaction happens to be 2. That means there are 2 molecules of Hi which are reacting per photon absorbed here. Okay. So, that is how do we account for a higher quantum efficiency greater than 1. Okay. It could be very large also. We may have a sequence of reactions wherein just with 1 photon absorbed you can have as many as about 10 to the power 6 molecules undergoing a reaction. There are the examples of that kind available there. Okay. So, that is what is meant by quantum yield. Okay. Now, how do we measure it? The question arises is that okay, we have understood what is quantum yield and what is the range of quantum yield, how do we account for low values or how do we account for high values, but the question is how do we measure it? The measurement essentially involves that we need to have 2 things to be measured. The first one is we need to have some means of measuring the concentration of the product which is found or the concentration of reactant which has decreased, either way. And second thing is we need to know how do we measure the amount of radiation that is absorbed. So, there are 2 things to be measured, because that is the quantum efficiency or quantum yield happens to be the ratio of these 2 things there. And typically as chemists we know how to measure concentration. There are a lot of ways of doing it. We can do it by chemical means or maybe we can do it by some kind of spectroscopic methods there. But how do we measure the radiation? That is very important here. That is what we are going to focus now on. And the measurement of radiation actually can be done by a variety of tools here. There are number of detectors available there. So, one of them happens to be a photodiode here or a thermocouple or a chemical actinometer. We will talk about the chemical actinometer. We will learn about the principle of chemical actinometer, how does it work and how does it help us to find out the amount of radiation absorbed in a photochemical reaction there. Okay. Let us see what is this chemical actinometer. Chemical actinometer basically is a chemical system that undergoes a light induced reaction. Basically, it undergoes a photochemical reaction at a given wavelength, and for which the important thing is we have to have a reaction for which the quantum yield is known accurately. That is the first premise for any chemical system to act as an actinometer. Okay, we will come to that, but how does an actinometer work? How do we make use of it? The principle of actinometry is as follows. What basically we do is we have this is a setup for the typical photochemical reaction to be measured. What we do is what we have here is a source of radiation. The radiation is coming here, the radiation is made to pass through a lens, then through a monochromator. Monochromator is a device which selects out of the whole range a particular wavelength is allowed to pass through, rest of the wavelengths are held back there. So, monochromator, it gives you an output of radiation of a particular wavelength. So, for a given reaction, maybe if I need 300 nanometers, so I use a monochromator which gives me an output of 300 nanometers. Then what do we have is, we have some kind of a thermostat here, and this is the reaction vessel here. And thereafter, this is a transparent reaction vessel. The light can pass through this, and then it can come down to a detector or an actinometer. Detector could be a photodiode or something else, or you use an actinometer. We are talking about an actinometer. Now, the process or the principle is as follows. What do? We start with this reaction vessel which is blank. That means it has only the solvent in this, no reactants are there. Then what do? We make the light of a particular wavelength pass through this whole reaction vessel for a certain amount of time, maybe 1 hour, 2 hour or whatever. Then thereafter, when the light passes through this, there is no absorption of radiation there, all the light transmits through this and falls on the actinometer. The actinometer detects that, it measures the amount of radiation falling on it. That is the part 1 of the experiment. Thereafter, what we do is, after having done that, we take our reactants in the reaction vessel now and repeat the whole process all over again. And then suppose my reactants are here, then I do the same exercise, I pass the radiation of the same wavelength for same amount of time, then part of the radiation will be absorbed, rest will be transmitted through there. So, the transmitted radiation will again get detected by the detector or the actinometer, and the two readings there, one when we had blank here, the second when we got reactants over there, the difference of the two gives me the amount of radiation which is absorbed by the reactants in the reaction vessel there. So, that is the basic principle of chemical actinometry. Now, let us see, let us take up a system which is typically used as an actinometer, and the system happens to be uranyl oxalate actinometer. It is a very commonly used actinometer. What basically it happens is, typically it consists of a mixture of 0.05 molar oxalic acid and 0.01 molar uranyl sulfate taken in water. So, that is a system we have. Now, let us see what are the reactions involved in this whole process whereby uranyl sulfate acts as an actinometer. The reactions are as follows. That is, the uranyl ions obtained from uranyl sulfate, they pick up photon and become excited, and each excited ion decomposes one molecule of oxalic acid to water and carbon dioxide. Suppose there are 100 photons absorbed, that means there will be 100 species of this kind, and each one of them will decompose one molecule of oxalic acid, that means 100 molecules of oxalic acid will be decomposed there. So, there is a 1-to-1 equivalence. So, what we do is, we start with certain concentration of oxalic acid, and then after passing radiation through that, we see what is the decrease in the concentration. This decrease in the concentration is a measure of the number of photons which are absorbed. So, that is the basic principle or basic premise or the rationale behind using uranyl sulfate as an actinometer. Okay. Let us take up an example to understand the application of this. Now, suppose there is a reaction like acetone. We know that acetone undergoes a photochemical decomposition in presence of radiation of about 300 nanometer. So, that is my reaction which I want to make measurement of. And to do that, what do? I use a uranyl oxalate actinometer having a quantum efficiency of 0.570 at 300 nanometers, and the objective is to find out the quantum efficiency of the reaction. How do we do that experiment is as I just explained, and the data obtained was as follows. That is, when we pass the radiation of 300 nanometer through the empty cell for 5 hours, it caused decomposition of about 1.550 into 10⁻² moles of oxalic acid. So, that is the first, that means we had a blank. The second part of the experiment was, we made the radiation pass through of the same intensity to pass through for same time through a reaction mixture, that basically we had acetone over there. We found that by this radiation passing through the system, 7 into 10⁻⁴ moles of acetone were decomposed, and accompanied by this we found that the unabsorbed radiation, that means the radiation which was not absorbed by the system, but was made to pass through, which was picked up by the actinometer, we found that the unabsorbed radiation decomposed 1.315 10⁻² moles of oxalic acid. So, that is the data. With that data, we are supposed to find out what is the quantum efficiency or quantum yield for the decomposition of acetone. So, that is our example to be solved. That is a numerical problem we are trying to talk about. How do we go about it? The first thing we do is we have to first find out what is the number of photons absorbed by actinometer with blank reaction vessels. That is the first data point we had. And how do we go about it is, we know that phi, we defined it to be equal to the number of moles of oxalic acid decomposed in the given time. In this case, it happens to be 5 hours. Then divided by the number of Einsteins of photons absorbed in the same time. Now, if I just rearrange this expression, I can get the number of Einsteins absorbed to be equal to number of moles of oxalic acid decomposed divided by the quantum efficiency. And substituting the data, what we find is the number of Einsteins absorbed will be equal to, this is the decrease in concentration of oxalic acid divided by the quantum efficiency. It comes out to be 2.719 into 10 to the minus 2 Einsteins. And we know that each Einstein of energy is equal to 1 mole of photons. So, we find out the number of photons to be equal to the number we got here multiplied by the Avogadro number. We get the number of photons which were detected by the actinometer happens to be 1.6373 into 10 to the power 22. That is when the reaction vessel was empty. Then the second part was the number of photons absorbed by the actinometer when the reaction vessel was having reactants. We do the same exercise all over again. We find that as per the data number 3, we find that this is the decrease in the concentration of oxalic acid. Again, divide by the quantum efficiency, we work out the number of Einsteins here. Then multiply this number of Einsteins by the Avogadro number to get the number of photons which are absorbed by the actinometer when the reaction vessel contained the reactants there. That means, we can find out the number of photons which are absorbed by reactants to be equal to the difference of those two numbers here. This is when reaction vessel was blank, this is when reaction vessel contained the reactants there. Subtract this here and we find that the number of photons absorbed by the reactants happen to be 2.4808 into 10 to the power 21. So, that is one part of the experiment. That means, the denominator we have been able to evaluate. As regards the numerator, we have to just find out the number of acetone molecules which have got decomposed in the whole process. That will be given by the decrease in the concentration, or this data is given to us that in this whole process, when you pass the radiation for 5 hours, 7 into 10 to the power minus 4 moles of acetone was decomposed. That is given to us. Multiply it by Avogadro number to get the number of molecules of acetone which got decomposed here. So, this is what we got, the number of molecules of acetone decomposed. This gives me number of photons. To put together, I can get the value of quantum yield. Quantum yield comes out to be just 0.17. That means, this is my number of molecules of acetone which got decomposed. This is the number of photons absorbed in the same time. So, this gives me a quantum efficiency of 0.17, or we can conclude that the quantum yield or the quantum efficiency for the decomposition of acetone is found to be 0.17. Okay. So, that is as regards our actinometry goes. Now, let us move further and talk about what is meant by fluorescence quantum yield. What we just discussed was quantum yield of a photochemical process. That means, we had a reaction wherein the chemical reaction was subsequent to absorption of radiation, it is a chemical reaction we are trying to focus attention on. However, we know that it may so happen that you give radiation to a molecule, it gets excited and it relaxes down only by photophysical processes. It may not undergo any chemical reaction, and one possibility could be, let us take up the formation and decay of an excited singlet state in the absence of a chemical reaction. That means, what we have is, we have a molecule, we give radiation, the molecule gets excited, then it relaxes down either by radiative or non-radiative mechanisms, but it does not undergo any kind of chemical reaction. In such a case, let us see what happens here. The typical processes could be absorption, wherein a molecule here in the singlet state absorbs a photon, becomes excited, and this molecule in the excited singlet state can relax down with the emission of a photon here. This is the fluorescence part, or it can undergo internal conversion from a given singlet state to another singlet state here, or it can undergo intersystem conversion from a singlet excited state to a triplet excited state. So, there are all the possibilities. We just, that is why we discussed, we kind of reviewed or recalled the photophysical processes here. That is where we needed them. Okay. If this be so, what we can see is the rate of decay of the excited singlet state will be equal to, given by the following expression here. We have got a molecule in the ground state, we give energy, it becomes excited, thereafter it starts relaxing down. So, there are different mechanisms. One possible component of the rate of decay is Kf happens to be the rate constant for the fluorescence emission here. So, minus Kf into the concentration of excited singlet state, that is the contribution of fluorescence to the decay here. This is the contribution of intersystem crossing, that means some component will undergo intersystem crossing, and this is the contribution of internal conversion. If you just simplify it a little, what you get is this as the expression for the rate of decay of the excited singlet state. Now we define what is called as the fluorescence quantum yield. Fluorescence quantum yield may be seen as the ratio of decay of the excited singlet state by fluorescence and total rate of decay of excited singlet state, or in other words we can say it is the number of photons emitted divided by the number of photons absorbed here. And if we just put it into the expression here, we find that phi f is just to qualify that we are talking about the fluorescence quantum yield. Just put the expressions here and simplify, we get it to be equal to kf by kf plus kisc plus kic. So, that is the expression we have for fluorescence quantum yield. Let us move further and see what do we understand by quenching. But why do we talk about quenching? The reason for that is many times what happens is we find that the fluorescence quantum yield is observed to be much less than what is typically expected on the basis of the rates of reactions over there. Why so? The reason for that is, the cause of that is what is called as quenching. That means there are certain mechanisms in addition to what we just discussed as the photophysical processes, which are the ones which make the excited singlet state to get decayed here. That means what happens is, we can probably say the quenching to be a general term. It is a very broad term that refers to the decrease in the fluorescence intensity due to different non-radiative processes. That means you have a molecule which has got excited, it can relax down with the fluorescence emission, but before that happens it undergoes some other reaction whereby it loses its excited energy, the energy of it, and as a consequence it gets decayed. So, the fluorescence intensity will decrease. So, anything which contributes to that will be causing what is called as quenching the fluorescence of a given system. And there are three different mechanisms. One of them happens to be collisional quenching, second happens to be resonance energy transfer, and the third happens to be electron transfer. We will talk about the first two here. The first one is the collisional quenching. As the name suggests, in collisional quenching what happens is the excited molecule which it collides with an atom or a molecule and undergoes a non-radiative transition to the ground state. We can represent it as follows. That means this is my excited singlet state here. It collides with some molecule called Q, which is called as a quencher, and in this process the energy is transferred to Q, and the molecule which was excited here becomes, it decays to the ground state here, and this Q which picks up the energy relaxes down by thermal means there. That means this molecule which could have undergone fluorescence emission is not able to do so because of this collision, whereby the energy has been transferred to the quencher molecule. Q is called as the quencher here. And typical examples for quenchers are oxygen is a typical quencher, iodide ions or cesium ions. They are the common examples of the molecules which cause quenching of fluorescence of different kind of systems there. The second mechanism is called as resonance energy transfer. RET. RET basically is observed, it is very typical kind of process. There are two kind of molecules we have. One, a molecule which is having a fluorophore, that means a molecule which can undergo fluorescence. This molecule is my donor here. And then we got another molecule which is an acceptor here. And the requirement here is that the emission spectrum of the fluorophore, called as the donor, should overlap with the absorption spectrum of the another molecule called as the acceptor here. So, in this case the spectrum shown over here, what you have is this bell shaped curve here is the emission spectrum of the donor here, the fluorophore, and the other spectrum here shown here is the absorption spectrum of the acceptor. We find that there is a major region of overlap over there. As a consequence, what happens is this donor molecule which is in excited state gives out its energy to the acceptor, which gets excited in the process, but the donor has got relaxed down to the ground state here. That means this donor is the one which is supposed to give fluorescence, and because of this reaction, because of this energy transfer to an acceptor molecule, it is not able to undergo fluorescence. So, this basically is the second mechanism of quenching here. This is how do we show it by the in terms of an energy level diagram. So, these are the two energy states of the donor molecule here. So, the donor in the excited state here comes down to the ground state and this energy which is emitted here is picked up by the acceptor molecule. So, the requirement here is that the two energies should be matching, and that is the energy transfer will occur when the energy emitted by the donor and the one required for the acceptor to get excited should match. That means, this delta E should be equal to delta E A by H. That means, this is my delta E A, that is the delta E value for the acceptor to get excited over there. And as per Foster's theory of RET, resonance energy transfer, there are two requirements which must be met for this to be effective, and they happen to be: the first one, that is the donor and acceptor should be close by, they should be separated by a very small distance. If the two parts of the molecule are very far, the transfer of energy will not take place. So, that means they must be in the close vicinity of the order of a few nanometers. And the second requirement is the photon emitted by the excited state of the donor should be absorbed directly by the acceptor. There is no other mechanism involved in that. So, they are the two requirements for resonance energy transfer to be there. Okay. Now, having talked about these two quenching mechanisms, let us see how do we, because we see it from here with this discussion here, that quenching actually is not desirable, because a molecule which was undergoing fluorescence, because of these two possible mechanisms of quenching, collision or energy transfer, the molecule is losing its fluorescence. It is not a desirable phenomenon, but we can make this phenomenon of quenching to a positive application, to a usable kind of phenomenon, and that happens to be what is called as photosensitized reactions. So, photosensitized reactions are the ones which I just mentioned. They make positive use of the quenching phenomenon, which is otherwise undesirable. What happens here is, that is a molecule that does not absorb radiation by itself, it can be made to undergo photochemical reaction, because we know that for any photochemical reaction to occur, the molecule must absorb radiation, but it may so happen that the molecule is not able to absorb radiation. But if we want to do a photochemical reactions on that, what do we do is that we make use of a molecule called as sensitizer. The role of sensitizer is that this sensitizer actually absorbs the radiation and gets excited, then transfers this energy in a collision to the reactant molecule here, which now becomes excited and gets through a photochemical reaction. So, that is what is called as a photosensitized reaction. That means, we are doing a photochemical reaction, but we are using a sensitizer, a molecule which is doing the job of absorbing energy and transferring it to the reactant here. Let us take an example here. Typically, the photosensitized reaction between hydrogen and oxygen to give water in presence of mercury vapors. The reaction goes as follows, that is, we take a mixture of hydrogen, oxygen and mercury vapors and expose it to UV light. Hydrogen and oxygen are not absorbing UV light here. So, it is a mercury which is going to do the job here. This mercury vapor absorbs 253.7 nanometer radiation, which corresponds to about 471.5 kilojoules per mole of energy, and becomes excited here. We represent it by the following expression here, that is Hg plus H nu gives me Hg excited here. This excited mercury atom undergoes collisional quenching with hydrogen molecule and dissociates it. That is where the whole catch lies. What basically happens is that this mercury vapor which has got excited transfers its energy to hydrogen molecule in a collision and breaks this molecule into two hydrogen atoms here. And the important thing which you have to make note of here is that this mercury is called a sensitizer, and the important thing here is that hydrogen on its own does not absorb this 253.7 nanometer radiation here. It is getting this energy through kind of mediated by a mercury vapor, and that is acting as a sensitizer here. Now, one more thing we have to make note of here is, if you look at the dissociation energies, that of hydrogen is about 432 kilojoules per mole, that of oxygen is about 490.2 kilojoules per mole. And in this reaction we just talked about, that is the mercury absorbs radiation which is about 470 kilojoules. That means, it can decompose only the hydrogen molecule and not oxygen here. So, as a consequence only hydrogen dissociates, and thereafter this atomic hydrogen which is obtained, this initiates reaction with oxygen to form water molecules. So, that is the process we have, and this is a very common and typical example of a photosensitized reaction here. Now, it is time to sum up what we have done today. What we have done today is that we started by briefly reviewing the contents of previous sessions. Thereafter, we recalled photophysical processes, and having done that, we moved on to defining what is quantum yield and explained chemical actinometry as a method to determine quantum yield or quantum efficiency. Thereafter, we explained the phenomenon of fluorescence quantum yield and tried to differentiate between the quantum yield what we defined earlier and in the context of fluorescence quantum yield, which basically comes into play when excited molecule decays only by photophysical processes. Thereafter, we defined quenching and explained its mechanisms like the collision quenching and resonance energy transfer. Then we saw that how do these mechanisms account for this quenching phenomena, and then towards the end we explained a very important area of photochemistry that is called as photosensitized reactions, and we talked about, with the help of an example, we showed their significance over there. So, with this